Hi, welcome back. We are in the third chapter talking about current electricity. So now we have completed basically the understanding of what the current is, what is meant by current, and understanding Ohm's law from the point of view of the physics, where we talk about same as V is equal to IR. Similar to that, we talk about J is equal to sigma E, and we also defined what is a drift current. And based on the concept of drift current, we were able to find out the resistivity or in this case conductivity is actually you can find out from the micro parameters like n into E square by m into tau. So where tau is basically what we call mean time between collisions or relaxation time. Now what we want to find out is this J is equal to sigma E, how far is it applicable? So where are there any limitations on this Ohm's law? Where are the limitations? So in some cases basically Ohm's law does in some materials, it is not the limitations as such of Ohm's law, it is more of some materials do not obey the Ohm's law. So there are different kind of materials. So in what way they don't obey? Some of them are like, for example, okay, it is possible in what all different ways you can not obey Ohm's law. One of them is let's say you have whenever you talk about V versus I, if you plot, okay, this is V and this is I, if you plot, this should basically come something like this. If it can come like this, then J is equal to sigma E, or J versus E if you plot. If it comes something like this, then we can say that it obeys Ohm's law, okay, because it is a straight line. You can see it's like saying that V is equal to IR plus 0. So it's like Y is equal to mx plus c, where c is 0 and m is nothing but r, and x is this I and y is this v. So we are plotting between y and x, like v and I here. So these things basically are going to give us I mean r I versus v in this case also. So it is something that is passing through origin, and you have to have a straight line. So sometimes it is not so. Okay, so what happens is that it could be the different kinds of variations that are possible are like something like V may be basically linear in many scenarios, but slightly varies and goes out of the linearity in only some scenarios. Like what we say is something like this, for example. So it went straight like this, but later changed like this. So such a thing, I versus V, we will say is not linear. So it is kind of curved in the end. Okay, this is one kind of not basically being linear, some curve. Second thing is basically it is possible that your V and I, okay, whenever you apply V in one direction, it works in one way. In another direction, it works in another way. Like it conducts like this in one direction, conducts something else in another direction. Okay, in the sense that it doesn't behave uniformly when you connect the potential difference basically in one direction to the other direction. Okay, to reverse the polarities, it changes. So that kind of a thing also is not a Ohm's law. No, it's not obeying Ohm's law. These are some of the semiconductors and diodes. We call in electronics we call them as diodes. So diodes actually follow this kind of a characteristics. And there are also some of them which are even more interesting. They will kind of obey for some time and then not obey and then obey, something like this. Okay, this is basically called this. In this case, really, what is happening, you see, is that for a given V, there is no unique value of I. The relationship is not unique. It's not a function. So that means that for a given for let us say for a given I, there is one I here. For that I, if you see, there is one V here, there is another V here, there is another V here. So when such a thing happens, it is actually not obeying Ohm's law. Okay, in the sense that initially, okay, when voltage increases, current increases, then suddenly it decreases here. This is called a negative resistance region, negative resistance region. So some materials work like this. Okay, one of the materials which work like this is called a gallium arsenide. So which we use it for making LEDs and all. So these are all going to be useful when we get into electronics, studying electronics. So currently we should actually not worry about these things, though we have got to introduce you to the various things that are possible. But what we are going to study is either the completely linear relationship or an approximate linear relationship. Okay. So wherever it is not linear, then we will take only that part which is linear and work with it. So that is the kind of Ohm's law obeying things is what we are going to work on. Okay. So the next step what we are going to see is what is the meaning of this, what is the general values of the resistivity of various, so it's just information, what is the value of resistivity of various kinds of materials. So I said there are some kinds of materials like conductors, okay, conductors. And we have something called, I named something called semiconductors, and then we have insulators. Okay. They have different values, very different ranges. Now, even in conductor, from one conductor to other conductor, the resistivity changes. I told you, the resistivity is the value, the thing that which basically decides the nature of the metal. So that if the resistivity is higher, generally for a same geometrical shape, its resistance will become higher. Okay. So resistivity of conductors generally, okay, are in the range of, let us say, minus 10 to the power of minus 8 ohm meter. Okay. So I'm writing this ohm, okay, is basically unit of resistance. So whenever we talk about resistance R, and these things you have already read in the earlier classes, the R basically unit is, SI unit is like this, ohm, based on the scientist's name. So ohm meter is the unit for resistivity, rho. Okay, this is rho. So that is the order, okay, of magnitude. Some of them are 3 into 10 power minus 8, 7 into 10 power minus 15 to 10 power minus 8, like that they keep changing. Okay, so they are all conductors, metals mostly. Okay. Now when you go into semiconductors, there is a slight variation. Carbon, for example, is in the range of 10 to the power of minus 5. This is carbon, whereas germanium and silicon are in very different range. This is some 0.45, this is some 2300, some very arbitrary ranges are there. Okay. And then when you go into insulators, so they are very high on some, resistivity, they are very high. So resistivity of them is somewhat around 10 to the power of plus 5 to, it ranges to 10 to the power of plus 16. Insulators, rubber, wood, many of those things, air for example, they are all insulators, they are very high. So the range of the resistivity, if you think about it, goes from 10 to the power minus 8 to 10 to the power plus 16. So these are the kind of materials we have. So this is just for basically for your information to know how much can the resistivity vary in what are the items. Now the next question basically is, if you look at this resistivity, is the resistivity dependent on temperature in any way, or is it constant everywhere? Like for example, if you take a copper or a tungsten wire, at all temperature does it have the same resistance or same resistivity or different? So what they have figured out is that by experimentation we have figured out that the resistivity of the metals actually change with temperature. Okay. How do they change? Generally, resistivity, temperature dependence of resistivity is a very interesting phenomena, okay, which is also used for actually making sensors, okay, temperature sensors, etc. So temperature dependence on resistivity. So we know that temperature it depends on temperature. Now how does it depend on temperature? Mostly in conductors. When you increase the resistivity, you increase the temperature, resistivity increases. So why so? Let's think about it a little bit. So if you see, for example, we have this conductivity formula. Okay, now let me write the resistivity formula, which is just a reciprocal of this. Okay. Now, when the temperature increases, so what are the things it is dependent on? Look at this. It is resistivity depends on m and e square, which are like mass of the electron and charge of the electrons. That cannot change. So what can change is n and tau. N is the number of charged electrons basically in one volume, unit volume, and tau is basically tau is the time between, mean time between collisions. Now, when you increase the temperature in a metal, it would so happen that the electrons actually get speeded up and they start moving very fast. When they start moving very fast, they tend to kind of have collisions more often. Because of collisions being more often, the tau value keeps reducing. Okay, when tau reduces, rho increases. But n doesn't increase. That means just because you increase the temperature, number of electrons that is available for conduction, that doesn't change much. So hence what happens is when you increase temperature, rho actually, when you increase temperature, what happens? Tau decreases and then rho increases. So that is the scenario of what we call conductors. Okay. So now in that case, what is the relationship? How do we do this? How do we find out? How is it changing? Let's say if we change it by 20 degrees, how much does the rho change? So there is a formula for that. Okay, so it's a very simple formula. If you see that you take a reference temperature, at reference temperature T naught. Okay, let us say rho is equal to rho naught. At reference temperature T naught, we have rho naught. That means that we know value of that at one temperature, like let's say 0 degree centigrade. You can take the reference as 0 degree. I mean, there you can take some other reference also. Let's say 0 degree centigrade. So now, if you want to find out at a higher temperature, the formula is any temperature, not just higher temperature, rho T at some other temperature is equal to rho naught into 1 plus alpha into T minus T naught. This is the formula that you can use. It's a very straightforward formula. What we are doing is look at this. What we are doing is, in a sense, it is rho naught plus, okay, rho naught into alpha into temperature difference delta T. So in the sense that if you know this value alpha, okay, this value alpha is called as temperature coefficient of resistance. Means this is basically tells us that how much temperature, if you change, how much resistance will change, resistivity. Okay. This is a temperature coefficient of resistance for a given material. For different materials, it is a different value. For example, for copper, it is like something 0.0068, like that for copper. For tungsten, maybe 0.0045, something like that. Okay. So they have different values, this alpha. So this alpha tells us, the alpha is the temperature coefficient of resistance. So what you are doing is that you first take the temperature coefficient of resistance and multiply it with the difference in temperature. There is this alpha in delta T. Okay. So into the original temperature, if you give original resistivity, so that value add to this. So this is basically what we are calling as the rho at temperature T. So rho at temperature T can be easily calculated by using this formula. Most of these kind of formulas appear like this only, kind of a ratio formula this is. So alpha is the temperature coefficient of resistance. So its value is positive. Alpha is positive for metals. Alpha is positive for metals. Positive means what? That means if alpha is positive, then when you increase the temperature, alpha rho T also will be higher. If alpha was negative, then it will subtract from the original and hence you will get a smaller value. So alpha is negative for certain materials. So we call they are called thermistors or semiconductors. For semiconductors, alpha is negative. Okay, so there is very serious reasons for them being so. We will not discuss too much into it, but alpha is negative for semiconductors, but alpha is positive for metals. So alpha is negative for semiconductors. So given a certain value of alpha for a given material, now you can always find out for any given temperature what is the value of rho, okay, that is resistivity. So by knowing the reference resistivity. So this is one important scenario here is that in semiconductors, very important is semiconductors, same law holds good. However, what happens in a semiconductor is this: whenever you increase the temperature, when you increase the temperature in semiconductors, some electrons will come out of the atom into the conduction band. So they can actually keep moving, like it will start conducting. It will be like a free electron. They become free electrons. So once they become free electrons, now their n value keeps increasing when you increase the temperature. Whereas the total number of electrons are not so high when compared to our metals, and because of that the tau value does not change much. Means the collisions do not really have any. It's like saying that you are inside an extremely busy mall, and even if you actually when it is very busy mall, then if you try to go fast, even then you cannot really go very fast because you clash with somebody else. So that is the case of conductors. In the case of semiconductor, it is almost like a Wednesday mall. Like it's like nobody is there. Even if you add more people to it, it doesn't really make them collide with each other. It's more of just the increased number of people. So that is what happens here. N increases, and when N increases, automatically rho decreases. So rho decrease means resistance decreases. So just follow this logically one by one. If this happens, this happens, this happens, this happens. Like that kind of a following should happen in your head to be able to understand this. So though the formula is same for both semiconductors and the conductors, the alpha value will be different. And alpha for semiconductors is basically negative, and for conductors it is positive. Okay. So let's just solve one question to be able to understand this better. So take down an electric toaster uses nichrome for its heating element. An electric toaster uses nichrome for its heating element. When a negligibly small current passes through it, its resistance at room temperature, that is 27 degrees centigrade, is found to be 75.3 ohms. 75.3 ohms. So at room temperature, at T is equal to T1, basically 27 degrees centigrade, the resistance 1 is equal to 75.3 ohms. When the toaster is connected to a 230 volt supply, the current settles after a few seconds to a steady value of 2.68 amps. That means when you connect it to an voltage of 230 volts, the current that it draws in a steady state settles down to 2.68 amps. What is the steady temperature of the nichrome element? What is the temperature of the nichrome element? That is the question. Okay, what is the temperature? I will call it as T2 of the nichrome element when you connect it. And it is given that the temperature coefficient of resistance of nichrome is averaged generally is equal to 1.7 into 10 to the power of minus 4 degree per C, degree centigrade, per degree centigrade. So let's understand this question. There is this nichrome wire. So the nichrome wire is basically used for making heaters. There is this nichrome wire, and if you simply measure its resistance by passing a small current without really heating it up, so the resistance shows up in the room temperature to be around 755.3 ohms. That is one information given to us. Now let is connected to the 230 volt supply, and it is drawing 2.68 amps. So we are asked to find out it is at what temperature. Let's see whether it is possible to do it just by looking at these two. Alpha, of course, is given to you. So now what we will do is V by I will give us the resistance at a very high value. So we will say resistance at high temperature R2. What, because once you send the current, it will get heated up. So that heated up means it reaches certain high temperature. When it reaches high temperature, resistance also changes. So when resistance changes, it draws different amount of current. So that current, when it stabilizes, is this. That means how much the resistance has changed to, that we can say. So that is nothing but V by I. So we will say 230 by 2.68. This is the value of resistance that it changes to. Okay. So it changes to a resistance of 85.8 ohm. Now you see, cold resistance is 75.3 ohm, hot resistance is 85.3 ohm. Now we want to find out how much is the temperature to be able to for so that its resistance actually has raised. We know this formula, rho T is equal to rho naught into 1 plus alpha T minus T naught. Okay. Now this formula is written for rho naught, rho, but it could as well be written for R, because rho to R conversion is multiplying into L by A. Rho L by A is R. Now the L and A being same, it is the same nichrome wire, so we can actually simply write it as R. So RT is equal to R naught into 1 plus alpha into T minus T naught. Now what are the things we know in this? We know our second temperature, that is RT, okay, that is basically 85.8 ohms. R naught also we know 75.3 into 1 plus alpha is given to us 1.7 into 10 power minus 4. Okay, and then T minus T we don't know. T naught is 27 over. Okay, so however, so we can simply go ahead and calculate the value, okay, for T. So the T, when you calculate this, will turn out to be equal to, I hope you can do the basic arithmetic, and it will turn out to be equal to 847 degree centigrade. So that means the nichrome wire has got heated up to such a high value, and its temperature, its resistance has changed a little bit. Okay. So this is basically the how nichrome wire is used in many of the heaters. Even the geysers actually use nichrome wire. So when they get heated up, they change a little bit. So, this it is at 847 degree centigrade. So, this is how you can actually given the resistance find out the temperature. Given the resistance, finding out the temperature. Then it's like a very interesting thing you see. In fact, when you are actually working with certain nice metals which are having very steady value of alpha at all temperatures, you can use them to measure the temperature, because once you measure the resistance, it will tell us what its temperature is. So, even there is something called as platinum resistance thermometer, and platinum resistance thermometer is used to measure temperature using resistance of a platinum wire. So, temperature coefficient of resistance is used in these kind of applications also. So, let us just try one more question, okay, before we actually move on. So, take down the second question. The resistance of a platinum wire, of a platinum resistance thermometer at the ice point is 5 ohms and at the steam point is 5.23 ohms. That means at T is equal to 0 degree, I said T naught, it has I will call this basically R naught as 5 ohms. When this is 0 means temperature, this is, okay. And R 100 degrees steam point, it is 5.23 ohms. This is the two information given. So, you dip it and see it. Now, when the thermometer is inserted in a hot bath, the resistance of the platinum wire is 5.795 ohm. Now, we have got some other temperature that we are measuring. Okay, when we measure that temperature, it is showing me the resistance of 5.795 ohms. Now, question is, what is the value of T? What is this value of T? So, it's a straightforward question, but you have to apply the formula twice. Like here, the formula is, again you have first scenario is R100, is given to you, is equal to R naught into 1 plus alpha into 100. What I did was, I applied actually the same formula for two temperatures R naught, for temperatures 0 degrees and 100 degrees, because we are given R naught and R100. Using this formula, I will find out the value of alpha. Okay, alpha is known from this. Now, use the alpha and apply the next one. So, the alpha is nothing but R100 by R naught minus 1 into 1 by 100. I just transposed it for alpha. So, we got the value of alpha. Now, what we are going to do is, again we will say RT is equal to R naught into 1 plus alpha into T. So, the T we are writing is T minus 0, because the other one is 0. Okay. Now, in this case it is actually T is, we have to find out this T. So, RT, they have given RT. So, we just have to write everything for T. So, this is nothing but RT by R naught minus 1 into 1 by T, 1 by alpha. This is our T. So, look at this, RT by R naught minus 1 divided by alpha. This is our T. So, whereas alpha is known to us through that formula. So, I will substitute alpha here in this place, which is equal to R1 by R naught minus 1 into 1 by alpha. 1 by alpha is nothing but 100 divided by so 1 R100 by R naught minus 1. Okay. So, now this can be simplified, and when you simplify it, you will actually get it as basically take the LCM and cancel things, and you will get a very straightforward answer to that. So let me directly write what I got is nothing but RT, sorry, this is RT by R naught, RT minus R naught divided by R100 minus R naught into 100. This is what I got for T. Now, while I know RT, I know R100, I know R everything I know. So the moment you substitute it, I got this one as 345.65 degrees. So at 345.65 degrees, the temperature, at that temperature, it has actually raised to 5.795 ohms with this alpha for platinum. So if you have measured 5.795 ohms, that actually means that the temperature is 345.65 degrees. That is how the platinum resistance thermometer works. So we have understood how the temperature actually affects the resistance of any conductor metals. So we will not actually go into the detail of how the resistance affects the temperature affects resistance of semiconductor devices. We will wait till we go to electronics for that. Okay. Now we'll move on to what we call as electrical energy. Okay, what is this electrical energy? We'll talk about electrical energy and power. That is our next part. So we have seen about the energy in various mechanical aspects. Like for example, in mechanical energy we talked about potential energy, kinetic energy, and even in electrostatics we talked about potential energy. So now if you think of electrostatics, the way we define potential energy, so we can use that to define electrical energy. Okay, we want to define what is electrical energy and also power. How to define these things? So you know that, let us say there is a conductor, okay, and there are 2 points V1 and V2, some resistor basically, okay. 2 points V1 and V2. So now if the current is flowing in this direction I, okay, we can say that V1 is at a higher potential than V2. So the current is flowing. That means that the charges, what do you mean by current is flowing? Charges are going from here to here. The charges are flowing, positive charge is flowing from here to here, simply means that it is going down the potential gradient. So the potential energy, it is almost like the water actually coming from overhead tank to the bathrooms basically. So that is what is happening here. So now when it is moving, the charges, we can say potential energy of that has decreased. So the potential energy, how much it is decreased? Let's say change in potential energy, delta U. Change in potential energy. We call change in potential energy. So we will say delta U potential energy is equal to what? So that is nothing but, okay. So potential energy at this point is the Q into V1. Potential energy at that point is Q into V2. So I will say actually final potential energy minus initial potential energy. Final PE minus initial PE. That is the change, which means basically Q into V2 minus Q into V1. So because V1 is potential into charge is potential energy. So this is nothing but Q into V2. I will write it as V1 minus V2 and put a minus sign. We know that V1 is bigger than V2, which is nothing but V, let's say. I will write this as minus Q into V. However, we know one thing is that I is nothing but Q by delta T, or Q is I into delta T. So, I will write this as V into I into delta T. This is my potential energy, change in potential energy. We know that this is definitely negative. Change in potential energy is negative, less than 0. So, now we know what is our law of conservation of energy telling us. Law of conservation tells us that if potential energy is decreasing, then kinetic energy has to increase, isn't it? Kinetic energy has to increase. That we have seen that if I drop this at this point, basically this chalk piece has certain potential energy. Now, if I drop it, here the kinetic energy is 0. If I drop it, its potential energy is decreasing and kinetic energy is increasing continuously. Same thing happens here. The potential energy is basically decreased this much, means that much of kinetic energy has to increase. So, I would say by law of conservation of energy, delta K must be actually is equal to plus Vi into delta T. Then you add those two things, it will be 0. Okay, the change in kinetic energy should be is equal to change in potential energy. This is delta K, change in kinetic energy. But unfortunately, you realize that the kinetic energy of the electrons do not keep on changing like that. Kinetic energy of the electrons do not change. We know that there is a drift velocity, average drift velocity, and it is constant. You can find out the average drift velocity in a current flow. That means the velocity is not changing. It will set up a certain velocity and remain with that velocity. Though individual electrons have different velocities, I am talking on an average. The velocity does not change. If the velocity does not change, that means that kinetic energy, average kinetic energy, does not change. Therefore, delta K has to be 0. Now, what happens now? Delta K, if it is 0, then the law of conservation of energy will not be there. That is because the law of conservation of energy is not there within the electrical system. So, what is happening is the energy is getting converted into heat energy. So, the heat, this whole kinetic energy, delta kinetic energy converts fully into heat energy. And that we call actually electrical energy. So, if you want to light up a lamp, okay, you send current through that, and the kinetic energy of that is basically converted into heat energy. So, that the total energy is not delta W work done is nothing but V into I into delta T. So, that is our energy, total energy, and power is delta W by delta T, which is nothing but V into I into delta T by delta T, V into I. So, power is actually electrical power, what we call, is nothing but V into I. This is how we can prove how V into I. We have talked about how the potential difference. See, you think everything physically through the eyes of physics, electricity through the eyes of physics, because it is fundamentally a physics phenomena. So, when you go into electrical engineering, we don't get into so much of details. We get directly into power is equal to V into I. But how did it come? That's what you see here. Okay. Now, this can also be written by basically writing it as V is equal to anyway IR. So, if you substitute that here, okay, you will get it as P is equal to I square R. Power is I square R. So, I square R component is like that we say, okay, power. Now, generally what we talk about is the power dissipated by the resistance is I square R. Dissipated means what? This heat, it has gone as heat. So, if you talk about, for example, transmission lines are, let us say, coming from very long distances, and it has a certain resistance. Now, that resistance and the current, there will be very high current also going through that, and hence the I square R loss for such transmission lines are very huge. So, we have to reduce that loss. Otherwise, the whole of the electricity that is produced in a hydroelectric power station or any power station, when you distribute it, it will basically have a huge percentage going into heat losses. So, to avoid that, what you do is you have to minimize that. We want to minimize this. Let us say if RC is the resistance of the conductor that is coming from the power station to here, okay, and it is having a current of I, then I square RC is basically power wasted by the conductor. I want to minimize this. So, what is this I? This I is the total current, and it is the total power delivered, including the power delivered to your homes. So, let us say the total power delivered is P, then this I square is nothing but, so we can say for total power P is equal to VI, and hence I is equal to P by V, right? Total power delivered divided by total voltage. So, I am going to substitute that here, which is P square by V square into RC. So, for a given power that is delivered, what is the loss? Okay, that depends on, we can say RC definitely depends on, okay, because that is the resistance that is there in the distribution line. Okay. However, if you keep this V very high, the voltage very high, because of the V square factor here, that substantially reduces PC. So, this is nothing but our savior here. So, that is why what we do is, generally we do not actually send 230 volts or 440 volts like that, we send it 11,000 volts, 6,600 volts, like that we send very high voltages. So, this is why you step up the voltage and send it when you are distributing the power, and hence reduce the loss, power loss due to the I square R loss. Okay. So, that is basically an understanding of how this I square R loss works, power works. So, the next step that we are going to see is, so these resistances, if they are connected in series and parallel, how do they work? So, they are somewhat very straightforward. You have already kind of figured out even in the earlier classes, resistances in series and parallel. So, I will just quickly write it on how to derive effective resistances when you are putting it in series and parallel. Okay. If you take about, for example, two resistances in series and in parallel, so answers are very straightforward. Here I have one resistance R1, this is the symbol for resistance, this is R2. So, generally the voltages are added here, this is V1, this is V2, this is total voltage V, potential difference, and you can see that current that is flowing through this also is flowing through this, it is single current I. So, we know that V1 is equal to V is equal to V1 plus V2, and from Ohm's law we know the effective resistance. Suppose if I want to replace this whole thing by a single resistance R, which has the same current I. So, what is that value of that? That is what we are trying to do. So, IR is equal to IR1 plus IR2. This is Ohm's law. So, hence R is equal to R1 plus R2. So, when resistances are in series, you just basically add them, and it is not limited to 1 and 2. When you can say R is equal to R1 plus R2 plus R3 plus ... anything. So, this is resistances in series. So, resistances in parallel, this is series. So, resistances parallel. So, you need to basically understand in the case of resistances in series, the definition of series is not geometrical, okay, it's how you connect them. Like for example, this is the terminal 1 of one resistance, terminal 2 of other resistance, terminal 1 of this resistance, terminal 2 of this resistance. So the way we are connecting is the terminal 2 of the first resistance connected to the terminal 1 of the second resistance, and terminal 2 of the second resistance connected to the terminal 1 of the third resistance, and so on. And terminal 2, final one, will be connected to the voltage source. Terminal 1 for this one is connected to the voltage source. Whereas in the resistances in parallel, we don't do like that. We actually connect them like this. 1, 2, 1, 2, R1, R2. So terminal 1s are connected together and terminals 2s are connected together, and they are connected directly to the voltage source. So this voltage is common across R1 and across R2. The same voltage will be there. Now if they are same, what is different? Suppose if there is a certain current that is flowing through here, I, that current splits it here into I1 and I2. So current is different, voltage is same. So we can say current actually I is equal to I1 and I plus I2. Remember, this is simple derivations. This is like 2-3 marks easily will get. Okay, I is equal to I1 plus I2. Now I is nothing but V by R. So if the effective resistance is R, then it is V by R. And I1 is V by R1 plus V by R2, because V doesn't change. This is nothing but 1 by R is equal to 1 by R1 plus 1 by R2. So this is how the effective resistance can be calculated in the case of a parallel connection. So in fact, we even write it as 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3 as much as you want. This is resistances in parallel. So resistances in series and parallel, once you understand, then it is possible to look at what will happen if the resistances are having both series and parallel connections. How do you deal with them? So such things will come into picture. So we will actually do some problems on that when we go into live sessions. But understand that if you connect them in both series and parallel, for example, if you are connected one resistance here and connected two resistances here. So the way to do it is, let's say this is R1 and R2. This is R3. Is that this parallel resistance you can actually take and reduce it into a these two together can be replaced by its effective resistance. I will call this as R dash, okay, R dash, and now these two R1 and R dash can be again replaced by a single resistance R. So we know how to do this from parallel resistance to this one. We can use the formula 1 by R dash is equal to 1 by R2 plus 1 by R3. Once you do that, you will get the value of R dash. Now you calculate R dash. So substitute that R dash here. R1 and R dash are there, they are connected in series. Now you can say effective resistance R is equal to simply R1 plus R dash. If you have connected two resistances in three resistances, two in parallel and connected to a series here, this is how you go about doing it. What if, suppose if you connect two resistances in parallel like this, series like this first and then parallel? How do you work with this? In this case, let us say this is R1, R2 and R3. So here also it is the same thing. We will replace these two first with basically one single resistance. I will call it as R dash, and then R3 here. Now we take these two and then go ahead and replace that with a single resistance R. So here R dash is straightforward because R dash is simply equal to R1 plus R2. First we do the series. Now once you find out R dash, then calculating R is simple. 1 by R is equal to 1 by R dash plus 1 by R3. Like that, any combinations, any number of combinations of resistances can be computed. By using series parallel connections, you can compute any number of them. So what we will do in the next session is to understand that what is the meaning of cells, like how do we have power generators, and how do we represent them, cells, power sources what we call, and what happens if you connect sources or batteries what we call in series and parallel, what is the meaning of internal resistance. These are the things we are going to study in the next session. Thank you.